In this video, we will talk about magnetic materials. Now, there are many types of magnetic materials and magnetic phenomena, but here we will focus on the three most common. They are paramagnetism, diamagnetism, and ferromagnetism. In a paramagnetic material, if you look at the individual molecules or atoms, they are tiny magnetic dipoles. This is usually caused by either the spin or the orbital motion of an electron. When there is no external B field, and we look at the dipoles inside a paramagnetic material, what we see is that they are randomly ordered. They point in all kinds of different directions. And so on average, the net magnetic effect that they produce is zero, because some have fields pointing one way and some have fields pointing the other. And so eventually, on average, those components cancel out. So there is no external field and there is no internal field either. And the dipoles are present, but they are pointing in random directions, and they are disordered because of heat. Thermal energy makes them move, change direction, and point in various different directions. In diamagnetic materials, when there is no external B field, the individual molecules have no dipole moment. They are just perfectly neutral magnetically, and they are not polarized. So there's no dipole moment on the molecular level, and so no magnetization overall. In a ferromagnetic material, what we see is at the molecular level, there are dipoles. And if we look in small regions, what we find is that in these small regions, they are all aligned. They all point in the same direction. But neighboring regions could have different directions. So these regions are called domains. So this domain is pointing down. This domain has its dipole moments pointing like this. This domain has its dipole moments pointing like this. So if we were inside a domain, we would see some magnetic field, but overall, most macroscopic objects will contain many, many domains, and since they all point in different directions, the net magnetic field, again, is going to be zero. So ferromagnetic materials, for example, include materials like iron or steel. And what we see is that if there's no external field, then often these don't have their own magnetic field to begin with. They are unmagnetized overall. But what happens when we apply an external field? So now in all three cases, we have applied an external B field indicated by these blue arrows. So what happens? In the paramagnetic material, each of these dipoles likes to align with the external field. And so now instead of pointing in random directions, they all roughly point in the same direction as the external field. There's still a little bit of deviation here and there, and it depends upon the temperature of the material. The higher the temperature, the more the thermal energy, and the more they can wiggle around and go out of alignment. And the lower the temperature, the more aligned with the external field they are. Once they align with the external field, this ends up strengthening the magnetic field inside. And so the internal B field is in fact stronger than the external B field, because you not only have the external B field, you also have the effect of all these dipoles lining up and contributing their own B field in the same direction. M here refers to magnetization, which is the dipole moment per unit volume. And so, as we said before, if you increase the temperature, you increase the thermal energy. And they become somewhat misaligned, and the contribution from the dipoles goes down, and B internal gets closer to just B external. So the magnetization, uh, which is the talking about these internal dipole moments per unit volume, that decreases with increasing temperature. What about diamagnetic materials? Remember, when there was no external field, the diamagnetic material had no dipoles at the molecular level. But now when we expose the material to an external field, the molecules start to polarize, but interestingly in the opposite direction. So now there are all these induced dipole moments at the molecular level, and they are all anti-aligned with the external field. As a result, the internal total field is less than the external field, because you have the external B field minus the contributions from the internal dipoles. This effect is interestingly mostly temperature independent. And finally, what happens with ferromagnetism? Much like with paramagnetism, when you apply an external field, the internal dipole moments try to align. In ferromagnetic materials, remember, they are organized in domains. So domains which are already aligned with the external field start to grow, whereas those which are pointing in other directions start to shrink. Eventually, overall, there is a net contribution in the same direction as the external field. And so the internal field becomes much stronger than the external field. There are several relations used to describe magnetic materials and their responses. Here are a few. So first of all, magnetization is the total dipole moment of the material divided by its volume. So it's the density of magnetic dipole moments. B internal is equal to B external plus mu naught times the magnetization. So B internal is a sort of total B field caused by both the external field plus the contributions of the material's dipoles. Chi m is the magnetic susceptibility, and Km is the relative permeability. So what we find is, just like how dielectrics essentially change the value of epsilon naught by multiplying it by a factor of k, magnetic materials change the value of mu naught by multiplying it by a factor of Km. So Km is just a pure number, and it is called the relative permeability. And often this number is very close to 1. So often people just focus on how different it is from 1. And they look at chi m, which is the magnetic susceptibility, and that is Km minus 1. So far it might not be entirely clear how different ferromagnetic and paramagnetic materials are. So it helps to plot a graph of the magnetization versus the external field. With paramagnetic materials, as you increase the external field, the magnetization increases, and this happens in a linear fashion. If you start applying magnetic field in the opposite direction, well, then the magnetization starts going in the opposite direction as well, because again, the dipoles want to align with the field. So we have Km is greater than 1. B internal is greater than B external because of the contribution of the magnetization. And chi m is greater than 0 because Km is greater than 1. In diamagnetic materials, however, since the induced dipoles are anti-aligned with the external field, as you increase B external, if B external is in the positive y direction, the magnetization is now in the negative y direction. It's still a linear response, but now with a negative slope. So Km is less than 1 and chi m is less than 0. And the B internal is less than the B external. But now the real change happens in ferromagnetism. Km is going to be much greater than 1, and thus Km is going to be much greater than 1. And the B internal is going to be much greater than the B external. What happens as the external field changes in strength? Well, initially we start with no magnetization, and as we increased B external, the magnetization increased until it's saturated. At this point, all the dipoles inside the material have aligned. There is no more to be gained from increasing the external B field, and so the magnetization has reached its maximum value. So that's what this flat portion here is. And now we start decreasing the external field. And what happens? Eventually, the magnetization starts decreasing, but not as quickly as when it first went up. And even when we reduce the external field to 0, we find we have a non-zero magnetization. This is because the interaction between the dipoles in their domains is so strong that even without an external field, they want to stay aligned. So at 0 external field, we still have some magnetization. This is why if you magnetize a piece of iron, it will stay magnetized even after you've removed the magnet that you used. How do we get the magnetization to go to 0? Well, we start applying our external field in the opposite direction. And the magnetization, which is initially still positive, starts decreasing, and eventually reaches 0. If we then continue with having our external B field in the opposite direction, the magnetization now starts pointing in the opposite direction and then eventually again saturates. If we then start decreasing that, again we see that when our field goes to 0, there is a non-zero magnetization. This phenomena where the state of the system depends upon what happened to it previously, it depends on the path you took to get there. This is called hysteresis. So how does one actually reach the state of zero magnetization? It's not enough to come to this point, because if at this point you then turned off B external, what you would see is that the magnetization would start coming back. It would creep back a little bit. There are two ways you can demagnetize a ferromagnetic material once once you first magnetized it. One is that you repeat this cycle, this hysteresis curve, but you do it smaller and smaller each time. You go to smaller and smaller fields each time. So you will end up eventually coming to 0. Let me see if I can illustrate that. So we repeat a smaller curve and then yet a smaller one. And each time we see this hysteresis lag, but eventually we can shrink the curve until it reaches the origin. The other way that we can demagnetize the material is by heating it. Once we supply enough thermal energy, the domains start to, they stop being aligned with each other, and the net magnetization goes eventually to 0. In fact, if you heat a ferromagnetic material to a high enough temperature, it stops being ferromagnetic and turns paramagnetic. But once it cools again, it will turn ferromagnetic. But usually that will remove at least some of the magnetization. This is why it's important, if you're working with magnets, not to drop them or to heat them, because if you drop them, then you give them some thermal energy when they hit the ground. Or if you heat them, you give them some thermal energy, and that slowly demagnetizes the material. Once again, let's remind ourselves of some of the definitions. Magnetization is the dipole moment per unit volume. Mu is km times mu naught. Notice, unfortunately, there are many different mu's in this uh, page. This is total dipole moment. This is relative permeability. This is the permeability of free space. Yes, they unfortunately all refer to very different things. B internal is equal to B external plus mu naught M, and chi M, the magnetic susceptibility, is Km minus 1. So what are some typical values? Well, aluminum has a positive chi M because it is paramagnetic. Copper has a negative chi M because it is diamagnetic. This is why copper objects are not attracted to magnets. Oxygen has a positive chi M and is thus paramagnetic. If you have liquid oxygen, for example, it will gather between the poles of a magnet. But water, surprisingly, has a negative chi M and it is diamagnetic. Iron, being ferromagnetic, of course, chi M is much greater than 1. It's 200,000 for iron. Cobalt, not quite as impressive, but still 250 is chi M, and it's also ferromagnetic. So, as a reminder, a paramagnetic material, if you apply an external B field, the dipoles align with the external field. And the response to this external field, since the dipoles are aligned with it, is it wants to move to a stronger field. So if you expose a paramagnetic material to a magnetic field, it will be attracted to the region of the field where the field is stronger. This is because the dipoles can decrease their potential energy by moving to a stronger region of the external field. Here we are using the idea that the potential energy of a dipole in an external field is minus mu dot B, which is equal to minus mu, which is equal to minus the magnitude of mu times the magnitude of B times cosine theta. If the dipole is aligned with the external field, then theta is 0, and so you get minus mu B. And so the way to make this potential energy smaller is to move to a stronger field. In diamagnetic materials, the induced dipole moments are anti-parallel with the external field. So in other words, theta is 180 degrees. So you get minus 1 from here, and there's another minus here. So your potential energy is just magnitude of mu times magnitude of B, which is positive. So to decrease your potential energy, you want to move to a weaker field. In ferromagnetic materials, again, your dipoles are aligned with the external field. And so you want to move to a stronger field to decrease the potential energy. This is why ferromagnetic materials are easily attracted to the poles of a magnet. Now, remember we said that water is diamagnetic, and we said that diamagnetic materials move towards weaker fields. This can be used for magnetic levitation. And one of the most dramatic examples of this is using water. But we know that water is present in pretty much every living thing. And so let's take a look at a living object exposed to a strong magnetic field. Here, scientists are using superconducting materials to produce extremely high magnetic fields. And, well, for something containing water, They decided to use a frog. And there is a frog alive and levitating in midair because of the diamagnetism of water in its body. And various other living things.
There's no problem with putting a man to force a man by this magnetic levitation to fly in the air. So technically, we can do it with you without any problems. As you see, it's alive and moving quite happily. No tricks.
Incidentally, the main scientist behind this, Andre Geim, was awarded first an Ig Nobel Award and then a Nobel Prize years later for the discovery of graphene. That's it for magnetic materials.